All right, today we are decoding literally the foundation of life and, well, modern society. We're talking about organic chemistry, the language of carbon. Think of carbon as the ultimate foundational letter in our chemical alphabet. If you can wrap your head around how this one element behaves, you are basically unlocking the blueprints for everything from the DNA in your cells to the fuel in your car. It is an incredibly logical system once you see the patterns, and I am absolutely thrilled to walk you through it today. So, here's our roadmap for this explainer. 1. The magic of carbon. 2. Hydrocarbons. 3. Decoding the chemical names. 4. Functional groups. And 5. Organic reactions. Let's just dive right in. Section 1. The magic of carbon. Let's figure out exactly what puts carbon right at the center of the chemical universe.
Now you hear the word organic all the time, right? Like at the grocery store. But in chemistry, it has a super strict meaning. To be organic, a compound absolutely must contain carbon-to-carbon or carbon-to-hydrogen bonds. That is the VIP pass to the organic club. So things like carbon dioxide or calcium carbonate, yeah, they have carbon in them, but they completely lack those crucial CC or CH bonds. Because of that, they're stuck in the inorganic category. You gotta have those specific bonds forming the structural backbone.
So what's the actual secret to carbon's ability to build these incredible backbones? Well, it all comes down to a single number, 4. Carbon is what we call tetravalent. That means it makes exactly 4 covalent bonds with other atoms. No more, no less. Imagine carbon as a Lego block with exactly 4 connection points. Because it always wants to form 4 bonds, it can link up with itself and other elements to create these massive long chains, complex rings, just sprawling 3D structures. It's the absolute golden rule of organic chemistry.
And because carbon can build these infinite shapes, it literally builds our world. I mean, it forms the fuels we rely on for energy, coal, natural gas. It builds the food we eat, carbs, fats, proteins. We're talking medicines, plastics, synthetic fibers, and at the very core of our existence, the biomolecules essential for life, DNA and RNA. All of it, the whole shebang, stems from carbon's ability to form those 4 stable bonds. Moving right along to Section 2, Hydrocarbons, the basic blueprints. Now that we know carbon is our core building block, let's look at the simplest molecules it forms. As the name pretty much perfectly suggests, a hydrocarbon is a compound containing only carbon and hydrogen. That's it, nothing else. Carbon provides the structural chain or ring, and hydrogen atoms just kind of fill in all the remaining empty connection points to make sure every single carbon has exactly 4 bonds. The crucial thing here is how these carbons link together. First up, alkanes. These have only single bonds. And because they're held together entirely by single bonds, every possible slot is filled up with a hydrogen atom. We call this being saturated. You literally cannot cram any more hydrogen onto an alkane. The general formula is CnH2n plus 2. So if you have 1 carbon, double it and add 2, you get 4 hydrogens. That's methane. But what if the carbons form a double bond with each other? Well, those are alkenes, or a triple bond, those are alkynes. Since these carbons are sharing 2 or 3 bonds between themselves, there are fewer slots left over for hydrogen. We call these unsaturated, because under the right conditions, you could break that extra bond between the carbons, and boom, you suddenly have room to add more hydrogen.
All right, Section 3, decoding the chemical names. We've got our root structures, but how do we actually talk about them? We need some grammar rules.
Organic chemistry naming is amazingly logical, I promise. The prefix simply tells you the exact number of carbon atoms in the chain. 1 carbon gets the prefix meth, 2 is F, 3 is prope, 4 is bute. And then it just follows the standard geometry prefixes you probably already know. Pent for 5, hex for 6, hept for 7, oct for 8, and non for 9. Just memorize this little cheat sheet and you can instantly visualize the size of the molecule just by hearing its name.
So, how does this actually build a chemical name? We take the prefix for the number of carbons and we add the suffix for the type of bond. Meth means 1 carbon. The suffix -ane tells us it's an alkane, meaning it only has single bonds and is completely saturated with hydrogen. Put them together and you have methane. Following that exact same logic, a 2-carbon chain with single bonds is ethane. Now, what if that 2-carbon chain had a double bond? Well, we'd swap the suffix to -ene, making it ethene. See, it really is just molecular Lego.
Section 4, Functional Groups. Adding character. We've built the basic hydrocarbon chains, now let's modify them.
Think of functional groups like adding adjectives to a noun. It gives the molecule totally new properties. Replacing just a single hydrogen atom on a hydrocarbon with a new group of atoms completely transforms its identity. For instance, if you pop off a hydrogen and attach an OH group, Your molecule is now classed as an alcohol. Attach that OH to a 2-carbon ethane chain, and you get ethanol. Attach an NH2 group instead, you've created an amine. If you stick on a COOH group, you've suddenly got a carboxylic acid, like acetic acid, which is exactly what gives vinegar its sharp smell and taste. There are also aldehydes with CHO, ketones with CO, and amides with CONH, which actually form the vital peptide bonds in our proteins. The backbone stays carbon, but these functional groups completely dictate how the molecule behaves, smells, and interacts with the real world.
And finally, Section 5, Organic Reactions in Action. Let's introduce the verbs of our chemical language. How do these molecules actually interact and change?
The two most fundamental ways these molecules react are based entirely on whether they are saturated or unsaturated. First, consider a substitution reaction. This happens a lot with alkanes. Remember, alkanes have only single bonds. Every carbon slot is full of hydrogen. They are saturated. So if a new atom wants to join the molecule, well, there are no empty seats. An existing hydrogen atom has to be kicked out so the new atom can take its place. It's a direct swap. Like when methane, CH4, reacts with chlorine gas, a hydrogen is swapped out to form CH3Cl. On the flip side, we have addition reactions. This happens with alkenes or alkynes, the unsaturated guys. Because they have double or triple bonds, those extra bonds can simply pop open, creating brand new available slots. Atoms are just added right into the molecule, no kicking out required. There are a few other vital reaction types that literally shape our reality too. Elimination is the exact opposite of addition. Atoms are removed, forcing the carbons to form a double bond just to satisfy their need for 4 bonds. Then there's polymerization, where tiny organic molecules called monomers join hands to form massive chains called polymers. This is exactly how we manufacture synthetic plastics. And lastly, combustion. When organic compounds react with oxygen, they break down into CO2, water, and, crucially, energy. This is the exact reaction happening when you burn coal for electricity, gas for your car, or honestly, even when you digest food. It is literally the reaction that powers modern society.
We've covered a ton of ground today, from carbon's unique 4-bond structure to naming chains, adding functional groups, and seeing them react in real time. So, I'll leave you with this final thought. The next time you look at the fabric of your clothes, or check the ingredients in your food, or take a painkiller for a headache, ask yourself, can you spot the invisible carbon chains keeping it all together? Because now that you know the language of carbon, I promise you're going to start reading it everywhere. Thanks for joining me on this explainer, and keep exploring the incredible chemistry all around you.